Sorry. Didn't see you there. If you couldn't tell, I'm kind of over in my own lane. Okay, I'm kind of doing my own thing. Nah, I'm gonna do my own thing. Right? So, guys, what's going on? Guys, what's happening? Wait, hold on, I gotta set tags. I told him I gotta set tags, you know. I told him I gotta set tags on the YouTube live stream. If I don't set tags on the YouTube live stream, you know, it'll be very bad for the algorithm. If we don't have any tags in our country, how will anybody find it? How will anybody find the videos that we're talking about? I don't know how anybody will ever find the videos we're talking about if we never set any tags on them. You know, some of these lefties, they want to get rid of tags, they want to make everything the same, but without tags, how am I going to find the video? What do I do? What do I do if I can't set tags on something? Okay, what are the tags going to be? Study, physics, grind set, motivation, cool, epic, self-help, inspiring, because it's truly inspiring. The work that I'm doing, the work that we're doing, folks, the work that we're doing is truly inspiring, okay? Folks, I didn't say it. It wasn't me who said it, okay, folks? Just ask anybody. They'll tell you the same thing. They'll say, wow, it's so inspiring. It's the most inspiring thing I've ever seen, you know? Okay. For some reason, it's not coming out as good as it would be usually, okay? The Trump impression is not hitting in the same way, folks. Folks, it's not hitting in the same way, folks. It's not hitting in the same way. Okay. Do 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 do. Here we are, stuck by this river, you and I, in a do falling down, ever falling down. That song's really good, especially the Alva Naoto and Ryuichi Sakamoto version of it. That version is so good. Here we are, stuck by this river, holding on to a thing that's ever freaking falling down. It's ever falling down. Okay, folks. I'm gonna start using Trumpisms unironically. Okay, folks, it's the greatest thing that we've ever seen, okay? What are we doing? What are we doing today? Oh, God damn. Okay, there's nothing. Okay, you're probably hearing the fan in the background. What we're doing today, right, is we are... Dude, yesterday I did bicep curls for like the first time in a month. And it hurts to extend my arms. Like, I have to like have them eternally bent. Like, this is the furthest I can bend one of them without any pain anymore, and it's just painful. So I can't straighten. My right arm is even worse. Alright, so I can't straighten it. Left arm seems to be healing up, actually. Or maybe it's because I'm... Yeah, it's because I have this closer? No, actually, it's... I don't know. Whatever. But, okay. So what are we doing? Should I have this webcam on? What's up? What's up, folks? It's a more intimate view, you know? Only problem is I look at this monitor to do whatever you're seeing on the screen. So we'll keep this webcam on for now. I also no longer have the 4:3 aspect ratio, just because it's not convenient to constantly switch back and forth. The dream would be a 16:9 and a 4:3 monitor like next to each other, with my laptop being like the third whatever monitor that you can throw whatever on, but it's not realistic. That's not realistic, is it? That's not my name. Yeah, well, that's not really realistic. Okay. So what? So what the hell? So what? So what? So what the heck's going on, guys? So what are you saying right now? So what do you mean? What do you mean? So what do you mean? What are you talking about? There's a lot that I'm talking about, folks. Oh, fuck. Oh, I have to pay for the Google Domains thing? No way, dude. I have to pay for it in order for... Oh, for my website to be redirected to the right thing, I have to pay. No freaking way, dude. Do I solve this right now? Do I fix this right now? Should I? I feel like I'm gonna have to fucking bust out my credit card. Do 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 do. Actually, it's already there. God damn, brother. What the fuck? This is so lame. What is workspace? Google Workspace? Yeah, like, I'm surprised it's just not working, because it should work. Wait, it does work. Wait, what? Wait, it does work now? Wait, what? It's auto-correcting, though. Hold on. Close incognito. Let's open up a guest window. GuiloPaulo.com. Okay, it does work? Is it because I threatened to turn back on the subscription? I have no clue. But now just GuiloPaulo.com is working, it seems. But it's not working there? But is working here? Excuse me? What's going on? Guys, if all of you guys can go to GuiloPaulo.com. It's working. So is the www, of course. But, like, is it auto putting in the www? Real way to test is by going on my phone, going to Instagram, going to my bio. Well, I put www, so of course it's going to work. Okay, I mean, it seems to be working. It seems to be freaking working. Here we are. Yo, this watch is cool. You can play roulette on it? Is there an actual ball in it? Oh yeah, there is. That's really cool, actually. Holy shit. Priced at 269,000 euros. Never mind. Is it really that much to put a roulette ball in a fucking watch?
¿Quiero conocer a nadie?
This is your sign to convert your cheap compact camera to infrared and take dramatic black and white photos with it. Mine is from around 2010 and I paid 30 euros for it. The conversion is actually super easy, and I already made a tutorial about it half a year ago. The filter I'm using is the most basic 720 nanometer one, but it works very well for me. If you still need a filter adapter for your camera, just leave a comment and I'll send you a link where you can buy one. You could also 3D print one like me.
The fuck? Yes, I know, folks, I'm wasting my time. I know, okay. Yes, folks, I am wasting my time. Don't worry, I understand that. I'm watching a guy fucking drum.
And lifting, especially to get strong in the 5 to 10 rep range, and lower rep ranges even more, you build connective tissue strength and integrity. When you get on gear, especially some kinds of gear that you use, trend specifically, makes your muscles big and strong, and your tendons really weak and frail, and it multiplies your probability of injury.
Guys, is clearly the reason I got injured is because I'm on gear. It makes sense now. Guys, it all makes sense. Yes, I'm on gear and I'm still this small. Yes, I know what you're gonna say. Doesn't matter. Dude, my fucking bicep. Okay. Ooh. I'm gonna close that window because I don't want people to complain that a crazy person is on the street. A crazy person is in their kitchen. They're in their kitchen and they're complaining about electrons and the periodic potential. Okay, I'm gonna stop doing it. It's just fun to do though, but I'm gonna stop doing it. Not because of you, but because I want to stop. Okay, I forgot to take my certified fish oil today, Kirkland signature brand. You know, I used to really hate Costco, but now I'm kind of okay with Costco because it just offers cheaper things for like the mass public, but I mean They need to have like a Costco, but for like really poor people, you know. Then the normal Costco, which caters to like middle to upper middle class people, would be totally fine. But like locking it behind some membership subscription, which I know is like one of the core reasons why they can actually sell at a lower price. I took Econ 101. Okay, that's literally the only class I took in economics. But anyway, okay. Let's start looking. I'm gonna stop doing it before it becomes a habit, but guys, look, this chapter is very much not long. We can get through it. This and probably couple it with a little bit of ChatGPT help. Like, hey ChatGPT, explain this shit. Explain this shit. Hey ChatGPT, explain this. I'll turn on the music for you guys. Yeah, you guys should be able to hear that. Might turn it up a little bit more for the stream, just because it might be good to have that in the background while I'm reading. But anyway, okay. Should probably turn off the fan as well if I just close the window. Alright, there's no point in having air circulating around in a closed room. What the fuck? Okay. Let's use the mouse. I'm using it on top of my iPad, which like has a magnetic field, which is making it feel weird. Okay, guys. Oh, fuck my biceps, dude. Fuck. Okay, guys. Okay, ladies and gentlemen. Okay, folks. Okay. I'm gonna stop doing it. In chapters 9 and 10, we discussed the wave nature of phonons and solids and how crystal momentum is conserved, i.e. momentum is conserved up to reciprocal lattice vectors. Further, we found that we could describe the entire excitation spectrum within a single Brion zone in a reduced zone scheme. We also found in chapter 14 that X-rays and neutrons scatter from solids by conserving crystal momentum. In this chapter, we will consider this whole part is like K is equal to some blah blah blah. K is equal to something. K is something. Oh my god.
Diddy? Yeah, with your anus?
What a good song, man. That part is the fucking greatest part. Cause if it's one step forward and two steps back, why do I want to try for more? I don't wanna wait for something more. One life is just ring up, bro. Oh, damn. Shit is so good. Anyways, but yeah, that was because what? K minus K prime, we said that this is equal to G, which meant that K is equal to K prime. Something like this. We had some sort of relation like this. For some reason, my mouse is polling at a very undesirable rate right now. Okay, now it's better. Okay, but yeah, that was the whole point of that. Okay. Pretty sure we can actually just go back and then we can see the restriction. K prime minus K equals G, which means that the absolute value of K. I got it flipped up here. Flipped around, but yep. Okay. And we will find that similarly, crystal momentum is conserved in the entire excitation spectrum can be described within a single Brion zone using a reduced zone scheme. Oh. In this chapter, we will consider the nature of electron waves in solids, and we will find that similarly, crystal momentum is conserved and the entire excitation spectrum can be described within a single Brion zone using a reduced zone scheme. Electron waves, wow. We've seen a detailed preview of properties of electrons in periodic systems when we considered the one-dimensional tight binding model in chapter 11, so the results for this section will be hardly surprising. However, in the current chapter, we will approach the problem from a very different and complementary starting point. Here, we will consider electrons as free electron waves that are only very weakly perturbed by the periodic potential from the atoms in the solid. The tight binding model is exactly the opposite limit, where we consider electrons bound strongly to the atoms and they only weakly hop from one atom to the next. Okay, so we're basically doing perturbation theory. So we start with completely free electrons whose Hamiltonian is h0 equal p squared over 2m. The corresponding energy eigen, so this is just the kinetic part of it, no potential. The corresponding energy eigenstates, the plane waves k, have eigenenergies given by h bar squared, k squared over 2m. This is typical for some sort of solution infinite square well or something like that. I don't know. Now consider a weak periodic potential perturbation to this Hamiltonian, Vr, with V periodic, meaning that Vr is equal to Vr plus R, where R is any lattice vector. The matrix elements of this potential are then just the Fourier components. This is the expectation value of it going from K to K prime. Which is going to be e to the I k minus k prime dot r. Yes, because these states K can be expressed as exponentials, waves, basically, which are time dependent, right? It's a time dependent Schrödinger equation, basically. Yeah. Which is 0 unless k prime minus k is a reciprocal lattice vector. Thus, any plane wave state k can scatter into another plane wave state k prime only if these two plane waves are separated by reciprocal. I kind of want to make sure. ChatGPT, confirm my bias, please. Is this equation showing the expectation value of a state k transitioning into state k prime when in the presence of some periodic potential V? Transition amplitude from a state k to a state k prime under the influence of a potential V. Yes. Yeah, and because this is just a Fourier transform of this thing, then it's defined as that thing. Okay. Damn. See, these are the things that ChatGPT is kind of good at. Look at this. I only gave it this equation, and it's already pointing out that this equation is especially important in the context of nearly free electron models or within the framework of perturbation theory and quantum mechanics.
where these matrix elements determine the probability amplitude for scattering from one state to another due to the potential V. See, these are the things that ChatGPT is good for. Sometimes. Not all the times, though. And this is 0 unless k prime minus k is a reciprocal lattice vector. See equation 14.1. Yes. Yes. Oops. Thus, any plane wave state k can scatter into another plane wave state k prime only if these two plane waves are separated by a reciprocal lattice vector. We now apply the rules of perturbation theory. At first order in the perturbation V, we have ek equals e naught k plus this matrix element, which equals e naught k plus v naught. Which is just an uninteresting constant energy shift to all of the eigenstates. In fact, it is... Where's this footnote coming from? Probably from something over here? Yeah. In fact, it is an exact statement at any order of perturbation theory that the only effect of V naught is to shift the energies of all of the eigenstates by this constant, since the Fourier mode at g equals 0 is just a constant independent of position. Henceforth, we will assume that V naught equals 0 for simplicity. At second order in perturbation theory, we have E naught, yes. This is just a result. Boy, if you didn't know perturbation theory and you were just getting this, you'd be pretty fucked. I think it's fairly easy to just go over like the real bare bones what perturbation theory is by just being like, this is a result of the Taylor expansion of Schrodinger's equation or something like that. Where the prime means that the sum is restricted to have g not equal to 0. In this sum, however, we have to be careful. It is possible that for some k prime it happens that e naught k is very close to e naught k prime, or perhaps they are even equal, in which case the corresponding term of the sum diverges and the perturbation expansion makes no sense. This is what we call a degenerate situation, and it needs to be handled with degenerate perturbation theory, which we shall consider in a moment. Fuck, we're doing degenerate perturbation theory? What the fuck, brother? I already did this I'm doing this in one of my other classes, man. Don't make me fucking have to do this shit. To see when this degenerate situation occurs, we look for solutions of the two equations where E naught k is equal to E naught k prime, which is k prime is equal to k plus g. Yeah, I guess. First, let us consider the one-dimensional case. Since ek is about equal to k squared, the only possible solution of equation 15.3 is k prime equals negative k.
What the fuck?
Equation 15.3 E naught k equals E naught k prime indicates that the unperturbed energies of states with wave vectors k and k prime are equal. If we are considering a one-dimensional case with a parabolic dispersion relation, which is typical for a non-relativistic free electron model, then the energy is a function of the square of the wave vector k such that E naught k is proportional to k squared. Now for any given possible value of k squared, there are two values of k that give the same energy, k and negative k, since negative k squared equals k squared. This is because the energy only depends on the magnitude of k. Okay, first let us consider the one-dimensional case. Since ek is proportional to k squared, the only possible solution of equation 15.3 is k prime is equal to negative k. This means that the two equations are only satisfied. What the fuck? Oh. I thought someone just said hello? This means the two equations are only satisfied for k prime equals negative k, which is equal to n pi a. When k prime equals negative k, 15.1. Yeah. Whoops. Yeah, so it's some integer of the Brion zone. Scattering from Brion zone boundary to Brion zone boundary, the states at the two zone boundaries are separated by a reciprocal lattice vector G and have the same energy. This situation leads to a divergence in perturbation theory, equation 15.2, because when the two energies match, the denominator is 0. Okay, in fact, this is quite general even in higher dimensions. Given a point k on a Brion zone boundary, there is another point k prime, also on a Brion zone boundary, such that equations 15.3 and 15.4 are satisfied. To see this generally, recall that a Brion zone boundary is a perpendicular bisector of the segment between 0 and some g. We can write the given point k equals g over 2 plus k perpendicular, where k perpendicular dot g equals 0. Then if we construct the point k prime, okay, I don't really care, sure. Since equation 15.2 is divergent, we need to handle this situation with degenerate perturbation theory. Hopefully you've learned this in your quantum mechanics courses already. In this approach, one diagonalizes the Hamiltonian within the degenerate space first, and other perturbations can be treated after this. In other words, we take states of the same energy that are connected by the matrix element and treat their mixing exactly. In other words, we take states of the same energy that are connected by the matrix element and treat their mixing exactly. Treat their mixing exactly is a very woo-woo statement. I don't know what they mean by that, but yeah. By diagonalizing a matrix M, we mean essentially to find the eigenvalues lambda I and normalized eigenvectors of the matrix. Determining these is diagonalizing, since you can then write M equals U dagger du, where U ij equals vj I conjugate, and D is the diagonal matrix, yes. My brother, we're really fucking doing degenerate perturbation theory in this? God damn. Okay. Degenerate perturbation theory. If two plane wave states k and k prime equals k plus g are of approximately the same energy, meaning that k and k prime are close to zone boundaries, then we must diagonalize the matrix elements of these states first. We have k hk is equal to e naught k, k prime hk prime is equal to e naught k prime, which is equal to e naught k plus g, k prime is equal to vk minus k prime, which equals vg conjugate. K prime hk equals v k prime minus k equals vg, where we have used the definition of vg from equation 15.1, and the fact that v negative g equals vg conjugate is guaranteed by the fact that vr is real. Okay. Equation 15.1. Okay, yes. Yeah. Yeah, and our Hamiltonian here is a potential. Pretty much, yeah. Because our Hamiltonian is the... No, this is the kinetic part. Well, no, I guess our perturbation H prime, or H in this case. So H naught is the kinetic part. Our perturbation, we're saying, is the potential. So H will be the potential. So that's why this matrix element here is going to give us something that has a potential in it. Like, in the moment when I learned perturbation theory, I didn't understand a fucking thing about it. But one, watching another professor's lectures on it actually helped a lot. Two, I don't know why, but hindsight, it just makes more sense when you're looking at it again. I don't know why, but that just is the case. apparently one of my things was delivered. I'm gonna check it now though. Okay. Guys, we're being lazy. We're being lazy. Ooh. Well, yeah, what I was basically saying here is that our full... Actually, wait. Oh yeah, whatever. Where we have used a definition, blah blah blah. Now within this two-dimensional space, we can write any wave function psi is equal to a linear combination of our two states. Using the variational principle to minimize the energy is equivalent to solving the effective Schrodinger equation, which now we put our matrix elements. So we put this there. This is our other diagonal. This is going to be this. This is going to be that. And we multiply by some coefficients. This is going to be equal to the energy with some up to some coefficients. The characteristic equation then will be that. Yes, that equal to E. Wait, what the fuck? How do we get here? So we have E naught K. Oh fuck! It would just be so much easier to just do this by hand, which we're gonna do. Don't care if you can't see it, folks. Do not care. So we have E naught K. PG star VG E naught K plus G with some alpha and beta is equal to E alpha and beta. So we're E naught K alpha times VG star beta is equal to E alpha beta How did they go from equation 15.7 to equation 15.8? Okay, so we solved the characteristic equation, which is that each h is equal to lambda. So we take h minus lambda I, set that equal to 0. So we take the determinant of the characteristic matrix, set it equal to 0. Okay. Okay. Oh. Dun, 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 dun. Ay, ay, ay. Oh, I dropped my pen. Fuck. How am I gonna pick it up? It's like an exercise in stretching, dude. My biceps, like, seriously. Oh, it hurts to stretch out, man, but I think it's good to stretch it out. Ooh. Left side is easier to stretch it out. I think because my right side is, like, being bent, having to use the mouse, but okay. Right. So the characteristic equation determining E is then this, because this is just the determinant of this minus E, because E is basically our eigenvalues of this matrix. Simple case. K is exactly at the zone boundary. Simplest case we can consider is when K is precisely on a zone boundary, and therefore K prime is equal to K plus G, is also precisely on a zone boundary. In this case, E naught K is equal to E naught K plus G, and our characteristic equation simplifies to E naught K minus E squared equals VG squared, or equivalently, E plus or minus is equal to E naught K plus or minus V. I just didn't absorb any of that. Oh. K is precisely, therefore K prime is equal to K plus G. In this case, E naught K is equal to E naught K plus G. So then you have this squared, which is equal to, you move that over to the other side, it's VG squared. Or equivalently, E plus or minus is going to be equal to, yeah, you take the square root of both sides, so you have plus or minus. Because you move that over. I don't know if you can do that. I don't know if you can just move it out. I don't think you can do that, but sure, I'll believe that. Because if you expand this, you get E naught K squared minus 2 E naught K E minus E squared is equal to this. I'm not actually sure how you get that. Okay, sorry about that, folks. Just got some business going on, okay? We got some business going on. Okay. Okay, thus we see that a gap opens up at the zone boundary, whereas both K and K prime had energy E naught K in the absence of the added potential VG. When the potential is added, the two eigenstates form two linear combinations with energy split by plus or minus VG. Energies which are split by plus or minus VG. Oh, okay. Yeah, and that's why it's degenerate. Because they're energies, but they're split. We're so close, guys. We're so close. We just have to go through a bunch of fucking formulas. Let's do this, though. We've got this, guys. Pretty easy, right? Pretty easy, I gotta say. I've got to say. Bum 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 bum. Okay, in order to understand this better, let us focus on the one-dimensional case. Let us assume we have a potential Vx equals V tilde cosine 2 pi x over a, with V tilde being positive. Okay. So we have some periodic potential, basically. The Brion zone boundaries are at k equals pi over a and k prime equals negative k, which is equal to negative pi over a. So that k prime minus k is equal to g, which equals to negative 2 pi over a. Yes, k prime minus k is going to be k prime. Since minus k is defined by this, minus k is going to be positive. So we have pi over a. Oh, so we have negative pi over a plus, or negative pi over a minus positive pi over a, which is going to give us negative 2 pi over a. And E naught K is equal to E naught K prime. It's degenerate. So we have a periodic potential, and we have some Brion zone boundaries, such that K prime minus K equals G. And the size of it is going to be negative 2 pi over A. Or the size, the magnitude, is going to be the absolute value of this, which is going to be 2 pi over A. So, or the magnitude. Examining equation 15.7, we discover that the solutions when E naught K equals E naught K prime are given by A alpha equals plus or minus beta of 15.7. I guess because that'll give us like a square or whatever the hell. They'll end up giving us this or something like that with the coefficients. So then thus we get the eigenstates psi plus or minus equal to 1 over root 2, some normalization factor, k plus or minus k prime. And these correspond to e plus and minus respectively. Since we can write the real space version of these k wave functions as formally what we mean here is xk k, which is equal to e to the ikx, which is equal to e to the ix pi over a, because k is equal to pi over a, don't forget that. And k prime is equal to e to the negative I k prime x, which equals e to the negative I x pi over a. I thought k prime was equal to negative k in this case, so wouldn't it be negative pi? So wouldn't it be positive? I guess k is equal to pi over a. That makes sense. Negative I k prime is equal to negative pi over a. So then what the fuck? Wait, hold on. Let me write this out. So we have k prime equals negative pi over a, right? And we're looking at e to the negative I k prime x, which is going to be equal to e to the negative I negative pi over a times x, which is going to be e to the I pi over a e to the ix. How is this negative? How the fuck is this negative? What the fuck? Why is... Okay. This has to be a typo, man. It has to be the case that they're saying that k prime is equal to e to the I k prime x, which is then equal to e to the negative I x pi over a. This has to be the case. It cannot be anything else. Okay. Yeah, because you're just describing it with a wave. So there's no reason why this is negative. We discover that the two eigenstates are given by psi plus, psi minus, where psi plus is about equal to that, e to the I x plus, yeah, k plus k prime, where you're ignoring the normalization factor. Yeah, which is about proportional to cosine. It's about proportional to sine. Actually, yeah, with this, it would be about proportional to that. If we then look at the densities associated with these two wave functions, see figure 15.2, we see that the higher energy eigenstate psi plus has its density concentrated mainly at the maxima of the potential V, whereas the lower energy eigenstate psi minus has its density concentrated mainly at the minima of the potential. So the general principle is that the periodic potential scatters, okay, let's see, wait. The higher energy eigenstate psi plus has its density concentrated mainly at the maxima of the potential V. Yes. Whereas the lower energy eigenstate psi minus has its density concentrated mainly at the minima of the potential. Yes. Which would kind of make sense. So the general principle is that the periodic potential scatters between the two plane waves k and k plus g. If the energy of those two plane waves are the same, the mixing between them is strong, and the two plane waves can combine to form one state with higher energy, concentrated on the potential maxima, and one state with lower energy, concentrated on the potential minima. Yeah, if the energy of these two plane waves is the same, so what's this first case? K is exactly at the zone boundary. K is not quite on his own boundary. It is not too hard to extend this calculation for the case where K is not quite on his own boundary. For simplicity, though, we will stick to the one-dimensional situation. We need only solve the characteristic equation, 15.8, for more general K. To do this, we expand around the zone boundaries. Let us consider the states of the zone boundary. K equals plus or minus n pi over A, which is separated by the reciprocal lattice vectors G equals plus or minus 2 pi n over A. As noticed in equation 15.9, the gap that opens up precisely at the zone boundary will be plus or minus Vg. Now let us consider a plane wave near the zone boundary. K equals n pi over A plus delta, with delta being very small and n an integer. This wave vector can scatter into K prime equals negative n pi over A plus delta due to the periodic potential. We then have E naught n pi over A plus some periodic potential, so K, E naught K, where K is this at this point, is equal to h bar squared over 2m Where do they get the h bar squared from? Oh, it's from the definition of from way up here. Where is it? This. Yeah, because this is k squared, where k is equal to k prime. Yes. No, k prime is equal to k plus g. K is equal to k prime plus g? No, k is equal to k prime is equal to k plus g. Yes. Yes. The characteristic equation is then E naught k times E naught k prime. Well, E naught k minus E. What the fuck? Yeah, because you have this factor and then this factor. Plus delta squared. Okay, yeah, sure. Which simplifies into this Sure, I'll believe it. Or E plus or minus h bar squared and pi over a squared. Sure. This has to be a Taylor expansion, right? Or did they just pull it out? I think they just pulled it out. I think they just pulled it out. I think so. Yeah, I think they just pulled it out. Yeah, because this distributed into this would be 4. And then square rooting that cancels out the square. If you distribute this into that, blah, blah, blah. Note that for small perturbation, which is what we are concerned with, the second term in the square brackets is larger than unity. So for the second, so that for one of the two solutions, the square bracket is negative. What the fuck? Thus, we see that near the band gap at the Brion zone boundary, the dispersion is quadratic in delta, as shown in figure 15.3. The dispersion is quadratic. Why the fuck are there... I never actually thought about this. Why are there gaps in energy? I guess because energy is quantized. That's just so weird that the world works that way. Like, what the fuck? This is so stupid, having these gaps. It's just so weird, like, fundamentally. Like, why the fuck are there gaps? The general structure we find is thus very much like what we expected from the tight binding model we considered previously in chapter 11. As in the tight binding picture, there are energy bands where there are energy eigenstates, and there are gaps between bands where there are no energy eigenstates. As in the tight binding model, the spectrum is periodic in the Brion zone. See figure 15.4. Yes, and it's periodic. Basically the same thing. It's just plotted. Guys, we're almost fucking done with this. We're almost done, and then I gotta go to class. We're almost done with this, and then I gotta go to class. This is gonna take me 2 hours to finish the whole chapter. Great. Usually it takes me 2 hours to get like through half a chapter. In section 11.2, we introduce the idea of the effective mass. If a dispersion is parabolic, we can describe the curvature at the bottom of the band in terms of an effective mass. In this model, at every Brion zone boundary, the dispersion is parabolic. Indeed, if there is a gap, hence a local maximum and a local minimum, the dispersion must be parabolic around these extrema. Thus, we can write the dispersion approximately Bro, I forget all about the effective mass. God damn. For now, we just think of this as a convenient way to describe the parabolic dispersion near the Brion zone boundary. Nearly free electrons in 2 and 3 dimensions. The principles of the nearly free electron model are quite similar in 2 and 3 dimensions. In short, near the Brion zone boundary, a gap opens up due to scattering by a reciprocal lattice vector. States of energy slightly higher than the zone boundary intersection point are pushed up in energy, whereas states of energy slightly lower than the zone boundary intersection point are pushed down in energy. We will return to the detailed geometry of this situation in section 16.2. There's one more key difference between one dimension and higher dimensions. In one dimension, we found that if k is on its own boundary, then there will be exactly one other k prime, such that k minus k prime equals g. As described earlier in this subsection, these two plane wave states mix with each other and open up a gap. However, in higher dimensions, it may occur that given k, there may be several different k prime, which will satisfy these equations. My dog. In this case, we need to mix together all the possible plane waves. Blah, 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 blah. Do not care. I don't care. Ladies and gentlemen, I do not care, actually. I'm not going to read this aside, because fuck asides. It's aside, so why do I have to care about it? In the nearly free electron model, we started from the perspective of plane waves that are weakly perturbed by periodic potential. But in real materials, the scattering from atoms can be very strong, so that perturbation theory may not be valid, or may not converge until very high order. How do we know that we can still describe electrons with anything remotely similar to plane waves? In fact, by this time, after our previous experience with waves, we should know the answer in advance. The plane wave momentum is not a conserved quantity, but the crystal momentum is. No matter how strong the periodic potential, so long as it is periodic, crystal momentum is conserved. This important fact was discovered by Felix Bloch in 1928, very shortly after the discovery of the Schrödinger equation in what has become known as Bloch's theorem. Felix Bloch later won a Nobel Prize. Who cares? Bloch's theorem was actually discovered by a mathematician Gassic Floquet, so it seems like Bloch is a fucking poser. Bloch's theorem. An electron in a periodic potential has eigenstates of the form. This? Yeah, it's some periodic thing. Where UK is periodic in the unit cell K, or in the unit cell, and K, the crystal momentum, can be chosen within the first Brion zone. In reduced zone scheme, there may be many states at each K, and these are indexed by alpha. The periodic function U is usually known as a block function, and psi is sometimes known as a modified plane wave. Because U is periodic, it can be written as a sum over reciprocal lattice vectors. We already went through this, I'm pretty sure. This form guarantees, in fact, the function U is periodic in the unit cell if and only if it can be written as a sum over reciprocal lattice vectors in this way. This form guarantees that UK of R is equal to UK R plus R for any lattice vector R, therefore the full wave function is expressed as this. Thus, an equivalent statement of Bloch's theorem is that we can write each eigenstate as being made up of a sum of plane wave states K, which differ by reciprocal lattice vectors G. A sum of plane wave states which differ by reciprocal lattice vector G. Yes, plane wave states K, which differ by reciprocal lattice vectors G. Given this equivalent statement of Bloch's theorem, we now understand that the reason for Bloch's theorem is that the scattering matrix elements K prime, V, K are zero unless K prime and K differ by reciprocal lattice vector. This is just a Lau condition. As a result, the Schrödinger equation is block diagonal in the space of K. Block diagonal? How is this a pun? Am I stupid? Oh, block. In the space of K, and in any given eigenfunction, only plane waves K that differ by some G can be mixed together. One way to see this more clearly is to take the Schrödinger equation. and Fourier transform it to obtain, where we have used the fact that vk minus k prime is only non-zero if k minus k prime equals g. It is then clear that for each k we have a Schrodinger equation for the set of psi blah blah blah, although by this time it may not be surprising that the electrons in a periodic potential have eigenstates labeled by crystal momenta. We should not overlook how important Bloch's theorem is. This theorem tells us that even though the potential that the electron feels from each atom is extremely strong, the electrons still behave almost as if they do not see the atoms at all. They still almost form plane wave eigenstates, with the only modification being the periodic Bloch function and the fact that momentum is now crystal momentum. This theorem tells us that even though the potential that the electron feels from each atom is extremely strong, the electrons still behave almost as if they do not see the atoms at all. They still almost form plane wave eigenstates, with the only modification being the periodic Bloch function. When I started to think about it, I felt that the main problem was to explain how the electrons could sneak by all the ions in a metal so as to avoid a mean free path of the order of atomic distances. By straight Fourier analysis, I found to my delight that the wave differed from the plane wave of free electrons only by periodic modulation. The wave differed from the plane wave of free electrons. So when electrons are exposed to a periodic potential, gaps arise in their dispersion relation at the Brion zone boundary. The dispersion is quadratic approaching the zone boundary. Thus, the electronic spectrum breaks into bands with forbidden energy gaps between the bands. In the nearly free electron model, the gaps are proportional to the periodic potential of Vg. Bloch's theorem guarantees that all eigenstates are some periodic function times a plane wave. In repeated zone scheme, the wave vector can always be taken in the first Brion zone. Any self-respecting solid-state physics book should cover this material. If this is not his favorite, then that means it's probably really good. Ha 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 ha. Am I right, guys? Am I right, guys? Ha 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 ha. Anyways. Okay, get on this screen, please. Move you over there. Yep. Okay. Alright guys, that's pretty much it. Peace. I'm done. I got class in I gotta leave in 45 minutes or an hour. Okay.